So welcome back to the second lecture on mathematical structures. In the first lecture, we looked at magmas, and in particular, we looked at monoids. And since I'm presenting this second lecture as well, I thought perhaps I could present something that links nicely well with the first one. We're going to be looking at mathematical structures which are called neat semi-lattices. The name sounds long and technical, but that's because the definition is not so long. So there is a notion of a lattice which we might be able to touch on, and that notion is a bit more complex than what a neat semi-lattice is. Let me remind you what a monoid is. In a monoid, we have a set M, a binary operation, an identity element. Now, an idempotent is an element of a monoid that has the property that if you multiply that element by itself, so you consider A times A, you will get 1. Sorry, you will get A. Then an idempotent monoid is a monoid where every element is an idempotent. So every element has that property. And let's immediately give an example of that. And perhaps you would like to maybe suggest an example if you have one in mind. So we're looking for a binary operation on a set, which is associative and which has identity element. And furthermore, every element has the property that if you operate on the element with itself, it will give you back that element. Can you think of such an operation that when you operate one thing with itself, it gives you back that thing? Clearly, addition of numbers is not like that, right? Well, 0 plus 0 is 0, but we want every element to be such. So that will not work. Multiplication of numbers is not like that either. Anything else you can think of that might be like that?
Exponenting to the power of 1.
That's not a
that's not an operation. Okay, it's a specific.
Yeah, that's not a binary operation. Have you never seen an algebraic expression, something operated with itself being equal to the same thing all the time? Have you never encountered any such operation? Well, actually you have, but it's just that you might not be recalling right now which one it is. But as soon as I'm going to show you, you will agree with me. You've encountered it quite a lot of times. So as my set, maybe this will be a good hint. As my set, I'm going to take the power set of a given set X. And now we need to specify an operation. What operations do we know on the power set of a set X? I'm getting an impression that everybody knows the answer, but they don't want to say it because they think they will ruin the lecture. If you pick two elements of a power set of a set, right? What can you do with them? So what will they be? They will be subsets of X. How can we combine two subsets of a given set?
We could take the Cartesian product of A and B.
Well, then we will not have a subset of X anymore, right? Thank you. Thank you for that input. So if you give your answer in the chat, I'm going to assume that you don't want to be called by your name, and I'm going to refer to your name, and I'm just going to thank you without exposing your name. So thank you for that input. We could take union of sets, right, as our operation. By the way, what will be the identity element for the union? So remember that identity element is an element C, let's say, such that C union with anything else must give back that thing, right? And this must work both ways, but because this operation is actually commutative, it's sufficient to just have one. So which C fits this formula, that must be true for every A. Empty set, that's right. Sorry, it was written up on the chat, I think, before you wanted to say something, Chad. So the empty set. And of course, this is a monoid because union of sets is associative, right? So we've got the identity law there where our C is now the empty set. And we clearly have that A union B union C equals A union B and union of that with C. That's clearly the case. One can demonstrate that very nicely using these things called Venn diagrams. So you draw your sets as regions on a plane, and then you shade the area of the result of your operation. So you've got A, B, and C. You operate. You take union of A and B, and then you will have this shaded area, all of A and B, right? And then you further union that with C, you get the entire picture shaded, and that will be the same result as if you first shaded B union C and then A. But now this operation is, in addition to giving us a monoid, it actually gives us an idempotent monoid, where clearly A union A is always equal to A, and that's exactly our rule for being an idempotent element, right? And that's true for every A, not just for a single A. This is true for all the A's in the power set. So let me just say it in words here. For all A, that's an element of the power set of X. So this is one example we could consider. There is another example that's quite similar to this one, where again we take the power set, but instead of union, we take another operation, and you might now easily guess that that would be intersection. I would still like your input as to what will be the identity element for this operation of intersection.
X itself?
That's right.
Oh, sorry, not A. It is, okay.
It is X itself, yes. And I think it's also clear here that, okay, the thing is associative. If for union, associativity law corresponds to this Venn diagram, then for intersection, the corresponding Venn diagram would give me an area that is a common overlap of all three things, A, B, C, right? And then the order in which we intersect does not matter. And more precisely, the arrangement of brackets in this expression doesn't matter. We furthermore have that A intersected with A is always equal to A for all A in the power set of X. And so we get that this is also an idempotent monoid. Now, there is something else we know about the power set, and namely that its elements are ordered. So you could take two elements, A and B of the power set, right? And you can decide or ask a question whether A is a subset of B or not. So the elements of this power set are ordered, almost like if we take the monoid of, let's say, the monoid of natural numbers, right? There the elements are also ordered. In addition to having, let's say, addition of natural numbers, we also have ordering of natural numbers. One number can be less than another, right? Now, of course, this relation of ordering of subsets of a set is closely linked with both, in fact, the operation of union and intersection. And the way we can express this link is to say that A will be a subset of B if and only if A union B equals B. Okay? I hope it's obvious why this is so, right? So A and B being subsets like that, the union is this entire region. And now if it turns out that this entire region matches with B, it means that this picture should not have had any of the part that I'm going to color in with red. This couldn't have been part of the picture, because otherwise, if that was part of the picture, then the union would not match with B, right? And so this part of the picture being non-existent means that all of A entirely resides inside B, and in other words, A is a subset of B. Yeah. Okay, so it's quite clear why this equivalence holds. Now, this is very, very different from, let's say, operation of addition, where if we had defined A plus B equals B, right? If we had forced A plus B to equal B, like here A union B equals B.
Sorry, Prof, wouldn't that union be A?
Sorry?
Wouldn't that union be A?
No, why? I mean,
sorry, that intersection.
Yeah, if we work with the intersection, then it will be the other way around. Yeah. So
okay.
If we force something like this, that A plus B must equal B, that will simply result in A equals 0. And that's because we can subtract B on both sides, right? Something we can't do here. We can't subtract subsets. There is no notion of negative. I mean, there's no process of taking negative of a set like we can with numbers. So there are no inverses, in other words, for this operation. Remember this idea? I don't remember actually. Did we cover that? Let me quickly have a look at the notes we had from last time. So I'm wondering now whether we covered the idea of inverse of an element and hence define a group. Just trying to look through our previous notes. I don't think we have actually. So maybe I'm not going to go in further detail now, but in general, the reason why we can subtract B here is because this monoid is something called a group, which means that there are inverses for elements, which is not true for the other monoid we're considering on the left side. Okay, but now what I would like to do is to generalize this idea. From the example we're looking at, which is this example right here. From this example, I want to generalize the idea to an arbitrary idempotent monoid and see what happens. So let m.1 be an arbitrary idempotent monoid. Then define A to be less or equal to B if and only if A dot B equals B. Okay? And let's see what happens. Now, what does happen to the less or equal relation? We have a lot of nice properties that the less or equal relation has, right? Let's list a few of them. Well, the first property is that, let's call this P1. The first property is that it's a reflexive relation. So for every subset A of X, or maybe I should say, rather, to think in terms of elements of the idempotent monoid, for every element of the power set of X, A is a subset of A. This is called reflexivity. And then we also have something called transitivity, which says that for every A, B, and C, we have A being a subset of B, and that being a subset of C implies A is a subset of C. We furthermore have, we actually have quite a number of nice properties. One of the other properties we have is called anti-symmetry. For every A and B, if A is a subset of B and B is a subset of A, then this implies that A equals B. And let me just remind you that this upside down A means for every. It's just short form for every. This is the symbol for implies. So it's a logical dependence. It's telling me that if the left-hand side is true, then the right-hand side must be true as well. And now let's see if we will be able to derive these three properties in the general case of a relation that has been defined for an arbitrary idempotent monoid. So let's get started with it. So our first theorem would actually state that the relation defined above has properties analogous to P1 to 3. And maybe it will be convenient if I remind you the names of these as well, so we can refer to them later as well. So this is called reflexivity of a relation. In this case, it's the relation of being subset. This is called transitivity. And the last one is called anti-symmetry. Now let's see if we can prove this theorem. So first, let's start with reflexivity. We would want A to be less or equal to itself for every A, right? But that by definition, and let me also indicate here what this symbol means. This means if and only if, which is basically implication in both directions. It tells us that this being true gives us the other thing is true, and conversely, if the other thing is true, then this must be true as well. So the two things are true at the same time when they are true. And if one of them isn't, then the other one isn't either. So A being less or equal to A would mean what? Could you maybe help me to complete this? So if less or equal in general was defined this way, then what would it mean to say that A is less or equal to A?
A dot A is itself.
Okay, but that's exactly A being idempotent, right? So maybe we make a side note here. Reflexivity of this relation is equivalent to every element being an idempotent. That's an interesting fact. Now let's look at transitivity. So A being less or equal to B and B being less or equal to C would be equivalent to A being equal to, well, if I keep it the same way as I wrote before, it will be equivalent to A times B equal to A. No, equal to B, right? Yeah, that's what we had there. And B times C equal to C. Now remember what we want. We want to derive from this that A is less or equal to C. And let's expand what that means. So for A to be less or equal to C, that's equivalent to A times C being equal to C. If I want to get from here to there, because of these equivalences, this reduces to getting from here to there. So now the question is, can I get from here to there? And we can just perform some algebraic manipulations to achieve that. So let's see what we can do here. Well, maybe we can do some very basic substitution, right? We've got here B equal to that, and maybe we can just substitute that in this place. Let's see what happens, right? I'm going to just write the calculation on the right side here. So we'll have A times B times C equals C. Well, we want to get to this equality in the end. Anyone has an idea how to go from here to there?
Can we move the brackets?
Why not? The operation is associative. Remember, we're working in a monoid.
Yeah. Okay, so move the brackets to A dot open bracket B dot C, yeah? And then B dot C is C.
B dot C is C, indeed. I mean, sorry, B dot C is C, so we get here A dot C. And then combining these equalities, we indeed get equality of A dot C and C, right? Wonderful. So we wanted to, I mean, we now see that we do have implication this way. So that whole thing does imply this thing, right? And we wanted implication which way? We wanted this to imply that, but then it's just a matter of composing these implications. We go left to right, top to bottom, and then right to left to get our implication the way we wanted. So to explain it in words, if this is true, then we know this is true. Then thanks to this little computation here, we know this is true. But then if that is true, then this is true as well. So overall, combining all these steps together, we get if this is true, then this is true, which is what we wanted for transitivity. Did we use here the fact that the monoid was idempotent? Did we or not? I mean, previously, for the other rule, we had a very nice description. When does the other rule hold? Exactly when the relation was exactly when the monoid was idempotent. What about this argument? And this argument, which is basically this computation, right? Did we need to use, what facts about the monoid did we need to use? Did we need to use this idempotent monoid? If you look at this computation, that nowhere we use the identity that A times A is A, right? In fact, we don't even use existence of the identity element. We just use the associativity, right? So that's a funny fact that this thing seems to be true for every monoid, right? This transitivity rule. So we can write this down. Transitivity turns out to be true for every monoid, not necessarily idempotent one. Okay. Now let's look at anti-symmetry. So there we have A less or equal to B and B less or equal to A, and that of course is equivalent to A times B equal to B, and B times A equals to A, right? And from this we want to conclude what? We want to conclude that A and B are equal to each other, right? So let's see if we can conclude from there that A and B are equal to each other. And now that we're discussing this, I remembered that I forgot to mention one thing. I forgot to mention additional condition on a monoid in order for this to work. What is that additional condition? Well, that the monoid must be commutative. So let me go back here. And say that in this definition, when we say let this be an arbitrary idempotent monoid, let me insert here an arbitrary idempotent commutative monoid. Why do I want to insert that there? Because when the monoid is commutative, then AB will equal BA, and so them being equal to each other would imply that B and A are equal. So then we do get this implication. And that requires commutativity, right? So so transitivity was true for an arbitrary monoid, but this one is true for so anti-symmetry. Turns out to be true for every commutative monoid. Again, we didn't use idempotency there. Now, the reason why we prove this theorem is because these three properties of a binary relation, reflexivity, transitivity, and anti-symmetry, they define another mathematical structure, which is called a partially ordered set. A partially ordered set is a pair consisting of a set X and a binary relation less or equal on X, such that this relation is reflexive, transitive, and antisymmetric. So in this terminology, what we've proved above then shows that if I start with a commutative idempotent monoid, so I'm starting with something that's a commutative idempotent monoid, then it gives rise to another structure, in other words, a partially ordered set, where the set here is the same as the monoid, so the elements of that partially ordered set are the same, and we now discarded the operation on the identity element, and now we have a binary relation between elements of them. Maybe it is worth reminding you what a binary relation is. But I think all of you who are here already know that. A binary relation on a set X is a subset of X cross X. So if we call the binary relation R, then we write X R related to Y, when X, Y, the ordered pair, is an element of the relation. In our case, our R relation is the less or equal relation, so our notation XRY becomes X less or equal to Y. So we started with a commutative idempotent monoid, and we ended up with a partially ordered set. It's something interesting that's happening here. So from one structure, we are creating another structure. Now, let us explore the idea of partially ordered set on its own first, a little bit, and then we're going to go back to this relationship between idempotent commutative monoid and partially ordered set. So let's look at some examples of partially ordered sets. Well, obviously, the one we spoke of earlier, power set of a set with a subset relation, will be a partially ordered set. Another obvious example is the set of natural numbers with less or equal to relation. A third one, which is a very important one as well, again, the set of natural numbers, but now as your relation, take the divisibility relation. So what does that mean? A divides B means that there exists a number C such that A times C equals B. Okay. This relation is reflexive, clearly, right? And it's also transitive. If A is a factor, I mean, another way thinking about this is A is a factor of B, right? If A is a factor of B and B is a factor of C, then A will be a factor of C. It's also antisymmetric. If A and B are factors of each other, then they will definitely be the same number. There are many other interesting examples of partially ordered sets. There is also something worth noticing, that there's a nice way in which you can draw partially ordered sets. For example, the power set. We'll pick an example of just having two elements, or maybe three, but let's start with two. So if we have just two elements and we want to draw all possible subsets of a two-element set, the picture will look like this. Where I'm going to draw lines to indicate that one element is less than the other. Okay? But I'm not going to draw all the lines. I'm only going to draw the ones that's necessary to then reach every two related pair by a chain of lines. Like, for example, here I didn't draw that vertical line because I could get that by combining this line with that line.
Sorry, Professor, if I can ask a question on something you said. Am I forgetting how to do division, or wouldn't it imply that there exists C such that B dot C equals A?
And this is not division. This is divisibility relation.
Oh, okay.
This is not, there's nothing to do with A divided by B.
Okay.
So it's a strictly a vertical line. No? With a three-element set, the picture will become, so this picture is a square, and with a three-element set, the picture will become a cube. And with more elements, you'll get cubes of higher dimensions. So these pictures will be quite elegant in that case. So there we've got these elements, 0, 2, and 1, 2, and we've got these relations between them, and then we also have that one, and the top one will be the entire set, and that's how we get a cube. Now, what would be the drawing for the divisibility relation? Well, for the natural numbers, the drawing is fairly straightforward. We've got 0, then 1, then 2, then 3, then 4, and then it goes on like that, right? What about the divisibility relation? How does that one look like? If we allow number 0 as well, and all the other numbers, I mean, what would be the bottom element? What would be something that will be at the bottom of the picture? Any ideas? So that should be a number such that for every other number, you always have A divides that other number. Which number A is such that that number divides every other number?
1.
Definitely 1. So the bottom element here is 1. And now which elements will be right above 1? So something that is above 1, but that you can't fit anything in between. Let's experiment. What about 2? Can I have a number that 1 divides that number and that number divides 2? Clearly I can't, right? Okay, what will be the next number that will be right above 1? 3 maybe? What about 4? Well, 4 is above 2. It's not right above 1. There's something in between, namely 2. What about 5? Well, 5 is above 1. 6 is above both 2 and 3. 7 is above 1. So these numbers that I'm going to be getting right above 1, right? This layer of numbers. What are these numbers called?
Aren't those your prime factors?
They're the prime numbers, yes. because being right above 1 means that 1 is its own factor that's not equal to itself. This is exactly the definition of a prime number, right? So the picture of this partially ordered set looks like this. We've got 1 at the bottom, then it branches out into all the prime numbers, so they form the next layer, and then all the other numbers come, and the dependence is basically given by prime number decomposition, right? So that's a very interesting picture, and it's a very complex picture as well. Huh? So let's put in 8 as well here, just for the sake of picture being a bit more populated. So 9 will be here. So the powers of those primes will form chains like that, right? And then 10 combines 2 and 5, and so on. Okay, now that we have a little bit of intuition about partially ordered sets, and we see that the various ways of comparing things that we can have partially ordered set, including divisibility relation, which looks a bit different from less or equal and subset relation. Although, of course, subset relation and less or equal already look quite different from each other, because you see, for the less or equal relation for numbers, we have a kind of a chain, right? But for subset relation, we have cube. So the pictures are very different from each other. Now that we did that, let's go back to our story here. We were saying here we can get a partially ordered set out of an idempotent commutative monoid. What about backwards? If I got this partially ordered set, can I recover back? Can I go back here? Can I recover back my commutative idempotent monoid? Now, to answer this question, let's go back to the example which motivated to us to consider this partially ordered set in the first place. This was this example here, where we noticed that the subset relation can be defined in terms of the union. What about the other way around? Can we define union in terms of the subset relation? It turns out we can. And here is how. We have this little lemma about union. So let A, B, and C be elements of power set of X, where X is any set. Then it turns out that A union B will be a subset of C if and only if A is a subset of C and B is a subset of C. This should be fairly obvious why this is so, right? I mean, I don't think we should prove the lemma. It's quite clear that the lemma is correct, right? I mean, the union combines these two into one set, and that set is smaller than another one, and of course each one of them will be smaller than the other one. That gives this direction. And conversely, if each of them is contained entirely in C, then of course the union will also be contained in C. So we have the other direction as well. But now, for us, this lemma is quite useful, because if you look at this equivalence, on the right-hand side, you only have subset relation. You don't have union on the right-hand side. So this lemma actually enables us to define the union in terms of the subset relation, you see. So then we take this idea, and then we generalize this idea for arbitrary partially ordered set, and we are going to define an operation out of the partially ordered set as follows. So proof here is left as an exercise for whoever would like to complete that exercise. And we can say that inspired by the lemma above, given a partially ordered set X with less or equal, we define a binary operation, A times B, to be such an element of X. So we define A times B. Well, maybe I will say it slightly different way. So given a partial ordered set, X with less or equal being its binary relation, it doesn't have to be, of course, the usual less or equal for numbers. It could be an abstract partial order. Then for any two elements A and B of X, we define A times B to be an element of X such that A times B will be less or equal to C if and only if A is less or equal to C and B is less or equal to C. And that should be true for every C. Now, we're not claiming that this thing always exists. We're not claiming that such a thing always exists. But if it does, then we're going to call it A dot B. And perhaps the first thing we want to prove is that if it does exist, such thing is only one. There can be two of them, because if there are two of them, then notation will become ambiguous, right? I mean, the notation will not be precise anymore, right? So let's first prove that the thing is unique. Let's say there are two such things. So we've got A dot B, right? And then we also have, let's call this thing A dot prime B, okay? Both of them we know satisfy this equivalence, so maybe we write this out for both of them separately. So we have that, and we also have the other one, and remember, in both cases, C can be arbitrary. Now, somehow, from these two equivalences, we want to conclude that A dot B equals A dot prime B. Any ideas? So required to prove here is that A dot P equals A dot prime B. Any ideas how to do that? It's actually a very
would it be true to say that A dot B dot C is equal to C, and A dot prime B dot C is equal to C as well?
How do we know that?
Didn't we define earlier on that if we have A if we have A less than B or less than or equal to B, then A dot B equals B?
No, but that's a different dot.
Oh, it's a different dot. Okay.
There we started with the dot operation, remember? We started with the nidempotent monoid, commutative one, and defined relation. Here, we're starting with a relation and trying to build an operation out of it. And we know nothing about this operation, not even that it's uniquely determined, you see. So we definitely can't use that other equality we had before. But just by looking at these two things, get an idea what we could do in order to conclude that these two expressions are equal to each other. Or maybe we forget what we want to conclude. We just try to see what can we conclude from these two things. Is there anything we can, any way we can go forward with these two assumptions? Nobody has a suggestion? Remember, these two equivalences are true for all C. So if they're true for every single value of C, we could basically start choosing some specific values of C and get a lot of different consequences based on that. And so what do you think should be our first try? Which value of C should we pick at the first try to do something useful?
Could we try A dot B prime equal to C? Assume that that's true.
So we try C equals A dot prime B. Was that your suggestion, Chad?
Yeah, that was my suggestion, yeah.
Okay, let's try. Let's see what happens. So let's insert this thing in the place of C and just see what happens. And let's do that for both of the equivalences. So we copy them here. I'm going to replace every single occurrence of C with A prime dot B. Okay, so there we go. And now I'm going to insert this thing here, and every single time that I raised C. There it is. And there it goes. And there. And there. And here. Okay, let's see what we got. Well, if I look at this left-hand side here, this is always true by reflexivity, isn't it? The right-hand side is something strange, but what I do notice here is that this strange thing is exactly the same as that strange thing, right? And what I see here is, of course, something I would want to wish for, because if I can prove that A dot B is less or equal to A dot prime B, and I can also prove the opposite, then by anti-symmetry, I will get that A dot B equals A dot prime B, right? So this one is looking good, right? What do we do next?
Sorry, Prof. I'm just checking. On that second line, is it not supposed to be after the and? Is it not supposed to be B prime is less than A? Prime B less than A prime B?
It's supposed to be what, sorry?
Is it not supposed to be prime B is less than A prime B?
We never had B prime. We had A and B. We didn't have B prime.
Sorry, I meant prime B. When I say in the second line, meaning so in the last line rather. In the last line we have here. After the and, is it not supposed to be prime B?
Like this?
Yeah.
What would that mean?
Okay, I suppose then I didn't fully understand the second line under uniqueness.
No, this is just prime has been inserted above dot. There are two different operations. So prime goes with not with B, but it goes with dot.
Oh, it's an oh, sorry. Okay. Oh, sorry. Oh, right. I thought that it was B that was primed, not the operation. Okay, so it's the operation that's different, not the entity.
We don't really even have an operation. I just wanted a different notation for another candidate for A dot B, and I denoted it A dot prime B. Maybe it wasn't very intelligent notation, but.
I also haven't been the smartest today, so I didn't notice it was the operation.
Okay, so what can we do from here? So let me repeat again what I said before. So we have that this thing always holds, right? Because by reflexivity, do you agree with that?
Yeah.
And this thing is something strange, but at least it's identical to what we put there. And being identical, of course, it means that they're equivalent to each other, right? But then, can't we combine these equivalences? So if this is always true, and that's equivalent to this, which is the same as that, and that's equivalent to that, doesn't it mean that this is always true? Do you agree with that, Chad?
Yes. So I'm busy thinking, but I'm trying to recall the definitions. With a I'm forgetting the words as well. What was sorry, Prof. What was the term that you used for if A dot A is equal to itself?
Idempotency.
For any monoid, is there only one operation that has sorry, not operation. Basically, I'm wondering if we had to suppose that B is equal to A, then that
Why
would
would you want to do that?
Well, I'm wanting to do that to try and, I suppose.
No, just a moment. Look, we proved that A dot B is less or equal to A dot prime B. But in the same, exactly the same way, we could prove that, or actually, it also follows from the same argument, basically, just swapping around the two, we could prove that this is less or equal to that, right? And then by anti-symmetry, A dot B will equal to A dot prime B, wouldn't it?
Sorry, Prof. I'm not seeing how you get that a dot prime B is less than or equal to A dot B.
I will get it in the same way as I got the other one. In the other one, the way I got this one, did it really matter which one was dot and which one was dot prime? They had symmetric roles, no? They were both satisfying. They were both solutions to this problem. They were both something that we could put here, right?
Yeah.
So if I manage to show that one of them is less than the other, then for the same reasons the other will be less than the first, no?
Oh yeah.
So basically, instead of substituting in the place of C A dot prime B, we will now substitute in the place of C A dot B. So we'll have here A dot B, 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 A dot B. And now this is true by reflexivity. This is the same as that. Therefore, this must always be true, and that's the one we wanted. Okay, so so we have uniqueness. This thing is, when it exists, it's always unique, right? And this allows us to define a function now which maps every pair AB to A dot B. And so we actually have binary operation on our set. And the next step would be, as you might guess, to show that this binary operation, in fact, will turn out to be commutative, idempotent, monoid. And so just like we created a partially ordered set out of a commutative, idempotent, monoid, it turns out we can go backwards as well and create a commutative, idempotent, monoid out of a partially ordered set. So, of course, when the dot A dot B exists for every A and B. So when A dot B exists, okay, so first of all, maybe I should make it clear that the proof of uniqueness is finished here, and I'm going to make it yellow because of the label here that was yellow. And then we can conclude here, so that when A dot B exists for all A and B in X, in M, forgot now what it was called. It was called X, right? When A dot B exists for all A, B in X, the dot is a binary operation on X. In other words, X with a dot is a magma, right? This magma turns out to be an idempotent commutative monoid, and let's prove that. So, associativity. I want to prove that A dot B dot C equals A dot B dot C. And perhaps I will employ a similar strategy as before. I will try to prove that this thing is less or equal to that thing, and then maybe using a similar argument also prove the other less or equal relation. Now we can think about this by kind of imagining this dot is union to help us with the intuition here. So if I'm saying here that, I mean, this is what I want to prove, right? This is required to prove. If I want a union of these two things to be included there, it's the same as saying that each of them are, right? So this will reduce to proving A dot B is less or equal to A dot B dot C, and proving separately that C is less or equal to A dot B dot C, right? Now, if only I could show that B is less or equal to B dot C, and similarly C is less or equal to B dot C, maybe that will be helpful for me to establish the rest. Why? Because, okay, so this is where the argument is going to get a little complex, and I hope that everyone will be able to follow, but if not, you can ask questions. So I'm trying to figure out how to prove this thing, and I'm noticing that I could maybe try to simplify my life if I first establish a lemma saying that something is always less than another thing that it has as a factor in both directions, this way and the other way. But perhaps not to be always worried about kind of changing the order of multiplication. Perhaps it makes sense if I first prove commutativity of this operation, you see. So I'm going to then revise my strategy here. Before associativity, I would want to prove the thing that we called commutativity in the context of a monoid. So let me move this down here and see if we can get commutativity. Okay, so there I want to prove that A dot B equals B dot A, right? But once again, it will be sufficient if I prove A dot B is less or equal to B dot A. And if I prove this for all possible A's and B's, then of course, then also we'll have that B dot A is less or equal to A dot B, and then by anti-symmetry, they will be equal to each other. But let's expand what it means for this to be true. So if you remember the definition of dot, it is something that fulfills this equivalence. So I'm going to copy it down here. So we know this thing is true for all C values, right? And I will try to prove that for the case when C equals B dot A. I didn't say correctly what I meant to say. So I don't want to prove this thing. This is just by definition of dot, but I'm just going to apply the definition of dot in the case when C equals B dot A. Then the left-hand side here will be the thing I'm required to prove, right? So then it will be sufficient to prove this bit here, which then becomes my lemma I wanted to prove before, right? Prove this and this. So maybe my idea for trying to first get commutativity wasn't a good one, because it seems like before we can get commutativity, first we need to establish these facts, right? And in fact, that is not so difficult to establish, because this thing, in fact, is equivalent to so let me recall the same definition of dot, but now I'm going to use it in the case when A is B and B is A, okay? So that's my definition of dot. And I'm going to replace my B here with A, because that's the case I want to apply it to. So B is replaced, A is replaced with B, and B is replaced with A, okay? What are we going to get? We're going to get that B dot A is less or equal to C, if and only if B is less or equal to C, and A is less or equal to C. Okay? And now I can insert in the place of C, I can insert B dot A. So all my C's go away, and I will get B dot A there. And something interesting happens. You see, this part, true by reflexivity, right? This is the definition of B dot A, so that equivalence is true. But this part is equivalent to that part. It's just the same thing, but with the two terms, that one and that one, rearranged. But we can definitely rearrange them when we're combining them with the AND clause, right? So these two things are equivalent. But remember, that thing was equivalent to that, which was equivalent to this, which is AB being less or equal to BA. So we did prove that AB is less or equal to BA. And we proved this for arbitrary A and B. So if I swap around, if I apply this thing for BA swapped around, then we will also get B dot A equal, less or equal to the other one. So then B dot A is also less or equal to A dot B. And by anti-symmetry, A dot B will equal B dot A. Right? Which is what we wanted to prove. That's the commutativity we wanted to prove. So maybe it's worth going through this one more time just to summarize. So we wanted to prove that, and we broke this up into two inequalities, this one and the other one. And we remarked that the other one will be a consequence of the first one once we prove the first one for all values of A and B. And then to prove this one, I recall the definition of A dot B. So this was by definition of A dot B. And that's equivalent to that. So A dot B being less or equal to C is equivalent to the other one for all values of C. We applied that definition in the case when C was B dot A. And then it simplified to that thing here. And then we recall the definition of this time B dot A, which was this, where in the place of C we inserted B dot A as well, just like we did there. And then we got the left-hand side here, which is true by reflexivity. The right-hand side matched, or at least was equivalent to the right-hand side there. And then eventually by chain of equivalences, because this is always true, we get this as a conclusion. So that takes care of commutativity. And now we will try to prove associativity, remarking that already from this illustrative rule here, we can already conclude something else that's going to be very useful. So in passing, we were able to prove as well that B is always less or equal to B dot A, and A is always less or equal to B dot A, right? This is always true. Okay, so why is that useful? Because here we wanted to prove these two expressions are equal. Again, we break it down into two inequalities, that one and the other one, which will be the same as this reversed. First, we take care of this one. So to take care of this one, we note that by definition of this dot here, for this to be less or equal to that, it means that must be less or equal to the other one and this one. And this is exactly what the rule says, right? So the definition of dot says that A dot B is less or equal to something when the first factor is less or equal to that thing, and the second factor is less or equal to that thing, right? So to prove that this is less or equal to that, it's sufficient to prove that the first factor, namely A dot B, is less or equal to that, and the second factor, which is C, is less or equal to that. Okay? Now, based on this note we made here, we do have that C is less or equal to B dot C, don't we? Anything is less or equal to, any factor is less or equal to the entire product. That's what this rule says, right? But this in turn is still, I mean, B dot C itself is a factor of that, right? So that will be less or equal to A dot B dot C, right? And we're combining this by transitivity, we get C is less or equal to A dot B dot C, which is what we wanted right here. So that part has been established thanks to transitivity. And now let's try this part. To do that, we're going to first prove a lemma. Our lemma will say that if B is less or equal to B prime, then A dot B is less or equal to A dot B prime, and that's always true for all A, B, and B prime. How will this lemma be useful? Well, we do know that B is less or equal to B dot C, because of this idea here, right? B is a factor of that, so that's by the note. And then we just apply the lemma in the case when B prime is B dot C. So the lemma will then give us the result we want directly, right? So it just remains to prove the lemma. But the lemma will be proved very easily, as you will see. Let's expand again the definition of A dot B. A dot B is less or equal to C if and only if A is less or equal to C and B is less or equal to C, right? And now let's take this definition and apply it in the case when C equals A dot B prime. What are we going to get? We're going to get A dot B is less or equal to A dot B prime, which is what we want to get in the end, being equivalent to A is less or equal to A dot B prime, and B less or equal to A dot B prime. So to get this, which is what we want, we just need to prove this part. Why? Because they are equivalent by definition of A dot B, right? If we look at this left side here, this is again by the note we made here. You see that a factor is always less or equal to the product. What about this one? How can we get that? Any ideas here? How can we prove this is the remaining ingredient? How can we prove that? Well, let's look at our assumptions, right? We have that B is less or equal to B prime. B is less or equal to B prime. We want B to be less or equal to this, but B prime will be less or equal to A dot B prime, again by the same note, right? By the same note here. You see, so B is less or equal to B prime by assumption, and B prime is less or equal to that. So by transitivity, we get that B is less or equal to A dot B prime. Okay, so once we confirmed this and that, we can now claim this is true, and that's exactly what we want to prove. But now that being true implies, so that's the lemma, right? And then we already explained how the lemma gives this, and we already explained why the other part is true. It was here. So these two things together, then by definition of that dot, this specific dot, gives us what we wanted to prove. And now we need to do the other way around, but that will be, in fact, derivable from this by commutativity. We will see that just now. So remember, we already know commutativity. So, and we also know that this is true for all ABC. So if we prove this, and we did prove that, right? If we prove this, then by commutativity we can rearrange the order of things, and so to prove that A dot B dot C is less or equal to A dot B dot C, which would be the other direction, the opposite to this direction. So we can then use anti-symmetry to prove this. We just note that we can rewrite these expressions by swapping the order. So the B and C can be swapped by commutativity, and then this whole thing can be swapped with A. So we get C dot B dot A equal to that, right? By swapping the order. And by swapping the order in the other case, we get C dot B dot A equal to A dot B dot C. And now if I insert these things there, so if I replace this thing with that, and I replace that thing with that, what will I get? I will get that this inequality we wanted to prove reduces to, so I'm just going to replace this with that, C dot B dot A being less or equal to C dot B dot A. And it's exactly the same rule, right? This is exactly the same rule as this. When brackets are on the left and we move them to the right, the element increases. We already established that rule, and so we have that for free then. And so these two together with anti-symmetry then will give that. So that's why it's sufficient to just prove one part. So this is thanks to anti-symmetry and star, where star is the remark we made there. So after a lot of effort, we proved that this thing is associative. We already know it's commutative. We just need to find an identity element, which might not exist, by the way. So that's another thing that I forgot to mention, that the identity element must exist. But we didn't make the claim about the theorem yet, did we? We didn't. I don't think we did. So we were just exploring what would happen. So if this thing does exist always, then we now prove that this magma will be commutative and associative. And let's prove idempotency as well, and then we will introduce identity element after that. So for idempotency, we would want to prove that A dot A equals A, right? And again, we split this into two parts, this inequality and the other one. But the other one, this one, we already have. We already know this is true. Would you like to remind me, how do we know that? Where does this follow from?
Well, if A is less than or equal to A dot B, and we know that A is equal to A, then if B is A itself, then
That's right,
it's
yeah.
equal to itself, and it's equal to
follows
itself.
from this rule, right, Chad?
Yeah.
Wonderful, well done. Yeah, great. Yeah. So we know that one already. So this is fine. We don't have to worry about that. We just have to prove this part. And once again, we employ the same strategy. We just expand definition. So A dot A being less or equal to C by definition of dot. So this is by definition is the same as A dot A being less or equal to C and A being less or equal to C, right? And this is true for every C, right? What do you think, Chad, which C we must take here to get to what we want here? Any ideas?
Oh, sorry. I was muted. I think if we assume that C is equal to A.
A very good idea. So if C was A, then what would happen? Then we would have this part, which is always true by reflexivity, right? And so that it gives us what we want. So this is true by reflexivity. And so we get what we want. So idempotency has also been established. Now let's try to see what happens with the identity element. So how to produce an identity element for this operation. So something would have to be identity element means that so the question we want to answer is when would dot admit an identity? So identity is an element such that times A, and now we know it's commutative, so we don't have to worry about the other direction. That times A equals A. That's what we know about identity element, right? Now, we do know that A is always less or equal to anything times A, right? So this is not the crux of the matter here, right? So it's this thing, it's this other inequality that matters here, because this one always holds, right? And we can expand this other inequality by definition of dot. It means that, so this is less or equal to A, means that 1 is less or equal to A, and A is less or equal to A, right? But this must be true for every A. For every A, this must be true. And of course, we want for every A what? We want for every A this to be true, right? But if for every A this is true, and for every A the whole thing is also true, then it means for every A this thing is true. This part is always true by reflexivity, so we get that for every A this thing is true. So we conclude now that identity, I mean, what does this say? It's an element that's the bottom element of the partially ordered set, right? The smallest element. So the identity element for dot is the one that is the smallest element of the partially ordered set.
Prof, can we call it our minimal element?
We cannot call it minimal because minimal means that there is nothing smaller than that. And this is stronger than minimal. This is something that's smaller than everything. We can call it minimum, but not minimal. Does that make sense?
Okay. Yes, it does.
Okay, now we can, after all this investigation, we can write down our theorem. Given a partially ordered set, which has smallest element and now I want to introduce terminology for the operation we define. So this operation, the one that's defined this way, is called join of two elements in a partially ordered set. Just like union, it's another word for union in a sense. So a terminology remark. This is called join of A and B, and is usually written as A with this symbol B, which is the same symbol we use for OR in mathematics, in logic. And the reason why it's the same symbol as OR is because OR will be an example of join in a suitable context. So has smallest element and admits joins, which means that for every two elements A and B, that joint thing exists. Then the set X with the smallest element, which we will denote by 0, not by 1, but rather by 0. Why? Because 0 usually is notation for smallest element in a partially ordered set. 1 is usually notation for the largest element. That has to do with the 0, 1 partially ordered set, which is of course important in computers. So this triple, X with the binary operation being join and the identity element being 0, is a commutative idempotent element. That's what we proved. We proved this theorem above. Let me make this a bit more explicit, clear. We proved this theorem in the discussion above.
Prof, would it be required or redundant to need to prove that the identity element dot the identity element is less than or equal to the identity element? Because we did prove it for all A, so I suppose the identity element would be part of that all.
Yeah, exactly. Yeah, we did prove it for all A, therefore we don't need to prove it separately for the identity element.
Would we at least have to state it though?
No, because we did prove it for all A. But I did make a mistake. What I meant to say here is a commutative idempotent monoid, not an element. Sorry. Being an idempotent monoid means that for every A dot A equals A. So what we've been able to achieve with this theorem is to go backwards. Starting with a partially ordered set, but not just arbitrary, the one that admits joins, right? And has smallest element. We can then go back. Does this, okay, let's now go back to what we did. Does this, so we have a bit more information about partially ordered sets now. Does this partially ordered set that we designed out of commutative idempotent monoid, does this one admit joins and have smallest element? Right? It's a natural question because we can go backwards when it does. So the question is, if we arrive from there, we want to go backwards, but then this must have those features that we need in order to go backwards, right? And let's prove that it's a separate theorem. Yes?
No, or a comment on that. Logically, it would make sense, but I'm not sure if in abstract terms it is true that you can have multiple minimums in something that's ordered. Meaning that you can't, logically, it doesn't make sense.
The question is, if we start with a commutative idempotent monoid, right? How do we know that this partially ordered set has the smallest element? Or how do we know that it admits joins? That's the question, you see. The partially ordered set created from a commutative idempotent monoid has smallest element and let's give a name to its notation to this commutative idempotent monoid. So I'm going to use slightly different notation now deliberately to make our symbolism match a bit more. So I'm going to denote this with a plus and a 0 for the identity element. So it has the smallest element given by 0, in fact. So the 0, the identity element of that monoid, will turn out to be the smallest element, just like in the opposite direction it was. Has smallest element given by 0, and does admit joins given by join of two things turns out to be the very same plus we started with. So not only will this theorem be telling us that if I begin with a commutative idempotent monoid, I'm going to get a partially ordered set with smallest element and joins. In fact, those joins and that smallest element, right, will match with the operations I started with. But that means that when I go back, right, I will get back exactly the same monoid I started with. Because remember, going back, join is the operation we design out of the partially ordered set, and the identity element for the join is the smallest element. So going back, I will get exactly the same commutative monoid I started with. So if I start with a commutative idempotent monoid, I get a partially ordered set, which then can be used to fully recover the commutative idempotent that I started with. And this holds not only just one direction, also in the other direction it will be true. I could start with a partially ordered set which admits joins and has smallest element, create a commutative monoid out of it, and then go backwards and design partially ordered set from it, and it will turn out to match with the one I started with. That would be a separate theorem, which we will probably not have time to prove, but even that thing is true. So there will be a nice correspondence between commutative idempotent monoids and partially ordered sets, where on a given set, where basically there's one-to-one correspondence between the two. So it doesn't matter which structure you satisfy, these two structures give rise to each other in a one-to-one way. It's a fascinating phenomenon sometimes when mathematical structures of very different kind, where here we have a geometric structure and there we have an algebraic structure. Structures of different kind turn out to encode exactly the same information in different ways. So let's prove this theorem. So we want to prove that 0 is the smallest element, right? But remember how less or equal was defined? We defined A less or equal to B to mean that A plus B, I'm now switching from dot to plus, equals B, right? That's how we defined it, right? Now, if I insert 0 here, this will be equivalent to 0 plus B equals B, which is true, because 0 is identity element, right? So this thing is true. Therefore, this is always true. Therefore, my 0, the one coming from the monoid structure, is indeed the smallest element. So that confirms the first part of the theorem. Now let's prove that the plus, the operation we start with, is actually the join. And remember, we already know that there is only at most one thing that fulfills the definition of join. We know it from here by uniqueness, right? So to prove that plus is join, we just need to prove that plus fulfills this equivalence. That's all we need to do. So let's see. So we would need that A plus B is less or equal to C if and only if A is less or equal to C and B is less or equal to C. But now this less or equal is designed out of the monoid structure, right? Okay, so we use the monoid structure to decode what we wrote here. So the left side here, this means that A plus B plus C equals C, right? And this must be equivalent to A plus C equaling C and B plus C equaling C, right? Let's get convinced of this. So we will prove this in two directions separately. So let's say this is true. A plus B plus C does equal C. Why would this make A plus C equals C? And separately B plus C equals C.
Would it be that if A plus B plus C equals C, then that implies that A plus B is the identity element?
It doesn't. It doesn't. If that was so, then the only thing that will be less than C will be the smallest element. It could be other things less than C. Remember, we can't cancel by C. You were telling me would X plus C equals C imply that X is identity element? It doesn't. This is equivalent to X being less or equal to C. So you were basically asking me whether this implies X is identity element. No, it could be many different X's that satisfy this, including C self-satisfies it, right? What happens if we add A to both sides of the equality? Or maybe we add B to both sides of the equality? Let's try a few things. So if we add A to both sides, I mean, this operation is associative, right? We do know the operation is associative because we've got a commutative idempotent monoid and commutative as well, so we can actually forget about the bracket. So if this equality is true, right, we can then conclude from here that A plus B plus C equals A plus C, right? Okay, but at the same time, the left side here is the same as A plus B plus C, right? Because A plus A is A, that's by idempotency, right? But A plus B plus C is C by the assumption. Oh, wow, look at this. I think we established what we wanted. A plus C equals C, there we go. This part has been established. What about this one? B plus C equals C. Maybe we can do exactly the same thing, but just this time we add B. So C equals A plus B plus C by assumption. And then we duplicate B. We write this as this way. And then we remark that just this part, I mean, we can separate the B out, so we get this. And we already know by assumption that that equals C, so we get B plus C. It works. You see, idempotency was very helpful here. Huh? And what about the other way around? If that is true and that is true, then surely A plus B plus C will equal, because of this will equal C plus C. Wait, sorry. Sorry, it will equal A plus C. And then because of this, that thing will equal C. So we're done. So we've proved both directions, and that's exactly what we wanted to prove. To prove that A plus B does fit the definition of join, and then by uniqueness we know that it must be joined. So the theorem has been proved. So this theorem tells us that when we begin with a idempotent commutative monoid, I create partially ordered set, that thing will have joins, will have smallest element, and the join will be plus the original operation I started with. The smallest element will be the identity element, and there is a reverse theorem which says that given a partially ordered set, having joins and smallest element, the partial order, sorry, the partially ordered set created from the idempotent commutative monoid X join 0. We already know that thing is an idempotent commutative monoid, remember? We proved that for every partially ordered set, this thing will be an idempotent commutative monoid. But now, being an idempotent commutative monoid, we can create a partial order out of it. But when we start with a partial order, we create a partial order out of this, the theorem says that we will get back to the same partial order. So the partial ordered set created from this thing will match with the starting partial order. And the final conclusion of these two theorems is then the following. We're now approaching to the end of the lecture. So the final conclusion of these theorems is that is a grand theorem that there is a bijection or a one-to-one correspondence. Maybe I'll use the other term. There is a one-to-one correspondence between commutative idempotent monoid structures on a set X and partially ordered set it's called partial order, okay, when we just think of this, when the set is fixed and we just think of the structure. And partial orders on X that admit joins and smallest element. And the very last conclusion is a definition. So we now arrive to the concept of that was supposed to be the topic of this lecture. But in fact, I realized in the process that I've given you the dual concept to what was intended initially. I'm going to change the heading in a moment. So a join meet semi-lattice is a partially ordered set admitting joins and smallest element. In other words, the exact thing that is part of the theorem. So another way of thinking of join meet, sorry, the meet shouldn't be there. A join semi-lattice, okay? Sorry about that. A join semi-lattice is a partially ordered set admitting joins and smallest element. And the previous theorem basically tells us that these things are essentially the same as commutative idem-bonded monoids. Okay. I'm going to now go back here and change the title to join semi-lattice. Now, a meet semi-lattice would be an analogous concept where, remember, we initially started with this example of join, and then we abstracted from there and derived this notion of join semi-lattice. If we had done exactly the same thing to meet, we would get the notion of a meet semi-lattice, and they will too turn out to be the same as commutative idem-bonded monoids. And when we want to abstract both of them at the same time, when we want to abstract joins and meets at the same time, so we want to keep them together, then the notion is that of a lattice. So that's what a lattice is. When it's a structure which will have both joins and meets at the same time. And that's why this name is complicated, because it's just part of the ingredient of that. It's just an ingredient of that structure of a lattice, where in a lattice we'll have both joins and meets, and here we just have one of them, namely join. Okay, so we kind of went backwards in this lecture. We introduced the structure at the very end, right? But we did look at the examples of commutative idem-bonded monoids, and so there will be examples of this structure. And going back here, we now know that this thing is a joint semi-lattice, right? And by the way, we also know that the partial order corresponding to it is the subset relation. But what about this example, the divisibility example? Is this an example of a joint semi-lattice? What would join be? What would be the smallest element? Well, we already said the smallest element is 1, right? Okay, so for it to be joint semi-lattice, it needs to admit joins. Can you guess what would be joins for the divisibility relation? So for the divisibility relation, a number join another number will be what? Of course, if you cannot guess, then we have to derive it. But I hope that you can guess, and then you will enjoy deriving it yourself after the lecture. I mean, not deriving it, but if you guess, you don't need to derive anymore, but proving that the guess was right, you can enjoy doing that yourself.
Suppose it would be the division of n and m.
The division of n and m, right? It results in something that's less than both n and m, doesn't it?
It would it
That's
be,
one problem. That's one problem.
The
other problem is that it's not sometimes not even defined. It has to be a natural number. What were you saying second time?
No, I was asking if maybe it has something to do with the c that comes from the division of a and b, of n and m rather.
Let's have a look at that. So what is the definition of join? N join m must be such a number that it divides c if and only if n divides c and m divides c. Whatever this join is, it must be such a number that things that are its divisors, things of which it is a divisor, right, are exactly those things of which both n and m are divisors.
Could it be the greatest common divisor?
Greatest
GCD?
common divisor will be greatest
Well, the
common.
join.
Yeah.
Well, I'm a bit confused in that when we talked about the division earlier, it wasn't the division that I was thinking of, but
It's
if
not
it was the
division, it's
division I was thinking of-
divisibility. So
okay,
this
yeah.
relation means that it's possible. Basically, it means that this is a factor of C. Okay, you can think of it like that. This will be a factor of those numbers, of which both n and m are factors.
Oh, it would be the subset, maybe? No.
Subset? What do you mean?
Oh, okay. Would it be the
Let's try. Let's try
union?
by hand. The union of numbers.
Oh, sorry, no.
So let's try 2 and 3. 2 and 3 must divide those numbers and only those that 2 and 3 both divide. If 2 divides 3, sorry, if 2 divides C and 3 divides C, if 2 and 3 are factors of C, right, then this number must be a factor of C. What is this number? Is it still not clear what factor means?
So I suppose, Prof, what's confusing me is the abstract way that we've defined division. So I wanted to suggest multiplication would be the join, but I wasn't sure about the way that we had discussed division.
It's not division, it's divisibility.
Divisibility, rather.
It's not an operation, it's a relation.
Okay.
We're saying here that C is an even number. And here we're saying C is divisible by 3. If C is divisible by both 2 and 3, then what is the single number?
C be 1?
Sorry?
Wouldn't C be 1?
But
Because that's the only...
how is 1 divisible by 2? You got the order switched around, I think.
C would C be 6? Would C be 6?
C wouldn't be 6. 2 join 3 will be 6, right?
Yes.
Yeah,
right.
There we go. We got a solution in the chat. It's the lowest common multiple. So you were very close, Zander.
I thought about it for a
second,
and then I realized I switched it around.
Yeah. LCM. So this example of a partially ordered set turns out to be also an example of a joint semi-lattice where the commutative idempotent monoid structure is the operation of LCM. And you might have learned or not learned that LCM is associative operation. And it doesn't seem to be so obvious intuitively, perhaps. But now we don't have to prove it separately because we proved it in general that join is always associative. So that's an application for us. Well, there is certainly much more to say about joint semi-lattices, but we will stop here. And if you have any questions, you can ask them now. Otherwise, I will stop the recording, and then we can, if you'd like to have further discussion after the recording. It seems like there are no further questions. Yes.
Prof, so what would C be in that case?
This is supposed to be true for all C, huh? C is
okay,
nobody.
for any C, okay.
Well,
and then
yeah.
Sorry, I just wanted to ask it. I don't even know if this question would make sense. But would that mono that we described, that mono that we described of M join and 0, would that have in it an equivalence class, and would union be in it?
I don't think I understand your question.
I don't think my question makes sense.
Okay. Yeah, I just wanted to say in conclusion that joint semi-lattices and lattices in general, I mean, we will definitely have a session on lattices, and then they lead to various different important structures from various different fields of mathematics. One of them is Boolean algebras, for example, which are very important for both logic and computer science. And a Boolean algebra will basically be an abstraction of the power set lattices of these kinds of things. These are examples of Boolean algebras, but there are other Boolean algebras that are different from this. But in many regards, Boolean algebra is very closely linked with these kinds of structures. But there are also many other avenues where you will find these joint semi-lattices, and so these are one of the most important mathematical structures. But then we'll see which one we'll have a chance to explore in this course. So thank you very much for your participation, for your input. I'm going to stop the recording here, and then we'll have the next lecture next week.